Okay. So now the next topic we're going to be talking about, the next couple of topics have to do with two particular specific types of power functions that have to do with linear functions and quadratic functions. None of what we're going to be seeing in these two topics, I believe, should be new to you guys. Linear equations, quadratic equations, you guys should be knowing these and working with these since secondary school. Or surely at least high school. But we're going to go through them because these are important topics moving forward in this math course, this sort of pre-calculus course. So let's talk about linear functions. How do we know that a function is a linear function? Well, a function is going to be a linear function when we have a power function. Remember that a power function is a function of the form f of x equals x to the n, where our power function, the value of n, which is the coefficient, is either 0 or 1. That's the highest value we have. And so if any of those two situations occur, we have what we call a linear function. And so basically there's two situations that we can have for a linear function. And well, why is it called a linear function? Well, surprise, surprise, because the graph of a linear function is a line, obviously. It is a line, okay? And so we basically have two types of linear functions. One is what's called a constant function, or what would be a horizontal line. And that's when we have the situation of f of x being equal to b, where b is a constant. So what we're talking about there is that, let's assume that b. So let's see, Anna, give me a number, any number you want, Anna.
4.
4, perfect. 4. So let's assume that b is 4. So in this case, let's say that b is 4. Then that would mean that y, which is equal to f of x, equals 4. And if we graph that, that would mean that we would have a line, a horizontal line that crosses in 4. Okay, that's one type of linear function where we have a constant. Then the other type of linear function is where we have we have different versions of this, or different models, but the generalized representation is a form f of x equals ax plus b, where a and b are constants, and obviously a is different than 0. In this case, we're also going to have a line, but that line is going to have a slope. I'm going to talk a little bit about that. One thing that's very important for a linear function, in the case of a linear function, the domain of the linear function is always going to be from -∞ to ∞. Okay. All of the real numbers can be a part of a linear function. Question. Let's see, Daniel. If the domain of the linear function is from -∞ to ∞, what do you think the range of the linear function is?
It would be from -∞ to infinite.
Correct. The graph is a line, and the line horizontally goes from -∞ to infinite. Vertically, it will go from -∞ to infinite as well. Okay. Is that the Sister of Black Widow poster that you've got next to you? Is that a movie poster? Oh, okay, that's cool. Where did you get that? That's huge.
Running like crazy from the security guard at the cinema.
This is being recorded, so that is going to be evidence.
No, I found it.
You found it.
In the movies.
Yeah, because sometimes the cinemas, they remove or take away the older posters and stuff, and they give them away. I've had that happen, and that is how you obtained that poster.
It's actually, I cut it here. Like it was me and a friend, so it was
You got half and half.
it was a prism. So here was Yelena, and in the back was Scarlett Johansson. So he took Scarlett, I took her,
Okay.
and there was another part that said like Black Widows in cines, and I cut that off because it was very big. But that was a mistake because now it doesn't have structural integrity.
It falls down. Yeah. Well,
Yeah.
just as a recommendation, you should frame it. There's these frames that are, it's not glass, it's just like a plastic thing. So you can frame it and it'll look very good hanging up there. That's a cool thing.
It's very big.
It is.
It's taller than me.
Oh, I thought it was resting on your desk. Oh, it's a standee. Yeah, I know the type. Yeah. Oh, cool. Cool.
Yeah.
That's cool. Have that there as inspiration. I'm actually I'm expecting today to get my Black Widow steel box. I collect all of the steel boxes of all of the Marvel movies, which has become a very complicated task since a while back. So I'm expecting the Justice League and Black Widow to arrive today, hopefully. Well, thank you for sharing that. Going back then, the range and the domain of a linear function are going to be the same. Now there's a concept of something called the slope. Now the slope is going to be a reference as to the inclination that our line is going to have. And the slope, that inclination, that is called the slope, is basically the relationship between the height and the length of 2 points that coincide in the line. And the height is called the rise, and the length is called the run. And it's actually the change in height related to the change in length. And the rise divided by the run, that's called the slope. And the slope is usually represented by an M. Okay, the slope is usually represented by an M. Okay. Okay. It's usually represented by that M there. I'm gonna, this is being recorded, and I know I'm gonna regret this, but I'm gonna do something for the Halloween activity. We're gonna do a bit of a contest. You guys don't know me or haven't been to my office because I haven't had an office I haven't been to my office from the pandemic, and but I love to collect things. So I have a huge collection of things that have to do with superheroes and a bunch of things. And it's gotten to the point where there are things that I don't have a place to put them in anymore. And I've got some duplicates because I'm very picky. If a figure or something loses something, I don't want it anymore and I want the complete version. So I'm going to dig up some of my collections that have these characteristics, and I'm going to give away some stuff on November 2nd. What is this stuff going to be? I've got some figures that I'm probably going to get rid of. If you Google Marvel movie collection, there's a thing called Marvel movie collection by a company called Planeta de Agostini. There are these ceramic figures that are hand painted, and I've got a few duplicates of those that have very small parts broken, but you don't notice them. I'm going to give those away, and my wife is going to applaud me for this, but I've got a bunch of, I'm going to say in Spanish, palomeras from Cinépolis and Cinemex, of anything you can imagine, those things that are heads. And so I think I'm probably going to be getting rid of some of those. So I'm going to take a bunch of things on November 2nd, and we'll give some of those away to good costumes and good explanations. And I'm going to, excuse me?
El tricky.
Yeah, it's gonna be something like, I know I'm gonna regret it because I'm that type of collector. I suddenly get rid of things and then I know I'm gonna want them back, but I know I need to get rid of a lot of these things. So we're gonna give some of those things away on November 2nd. Okay. Okay, now these are some examples of the linear functions and the concept of a slope. Now, if we're talking about the relationship or the change between the height and the length, that's represented like this. Usually the slope is represented, if we have 2 points, as the difference between the y divided by the difference in the x. So this would be delta y divided by delta x. Okay. Something very important for us to have a line, we only need 2 points in space. So 2 points in space represent a line. It's curious if you think about it, when you guys were doing the exercises in the last homework test that had to do with shifting 2 points, all of you, to visualize it better, assume that those 2 points connected in a line. And so if I have 2 points in space and I connect them, I automatically generate a line. And the same applies the other way around. If I want to create a line, I only need 2 coordinates. If I've got 2 coordinates, I can create or represent the line mathematically. Now, there's a few things here that are important. So these here are examples of slopes. So if m is positive, we're going to see a line that grows like this, or it's going to be inclined towards the positive x-axis. If m is negative, we're going to see a slope that grows towards minus infinite, and it's going to be slanted towards the negative part of the x-axis. A completely horizontal line, m equals 0. So the slope of a completely horizontal line is m equals 0. And a completely vertical line, m is undefined. Okay. And that's why, that's because in this case here, delta y, or the increment in y, is 0. And the increment in x can be whatever. And so 0 divided by a, this is going to be 0. In the case of this one, the rise in y is whatever number, but the rise in x is, or the change in x, I'm sorry, is 0. And we know that this is undefined. Okay, so we got to remember that. Positive slope, it's going to be rising. Negative slope, it's going to be rising, but it's going to be rising towards the other side, or decreasing, depending on how you interpret that. Slope 0 means a completely horizontal line. Slope undefined means a completely vertical line. And the expression to find the slope is the one that we see there. Now, having said that, then there are more than one ways to represent the mathematical model for a line. So one is the one that we talked about, which is actually this one here on the bottom, which is called the slope intercept, which is basically, it's the same one we saw at the beginning, but instead of m, we called this a. But actually the value that's multiplying the x is going to be the slope. So if I have a slope and I have the y-intercept, I can automatically create a line. The other more general representation of a line is going to be the point slope equation, where I've got a point and I've got the slope. And if I have a point, whatever point that crosses the line and the slope, I can automatically find the expression, mathematical expression for the line, and the slope is going to be given by the difference between y and the point that we're talking about, and x divided by x minus the point. So these are the different representations that we can have for a line or a linear equation or function. Now, usually this part here, this is where everybody starts to get confused in some of the exercises. And this has to do with the relationships. This has to do with the relationships that exist between slopes and the concept of something that is parallel and perpendicular. So when we're talking about something that's parallel, it's two lines that are parallel are lines that are never going to coincide. For that to occur, the two slopes have to be exactly identical. Okay, so the two slopes are, the two lines are parallel. That means they're never touching. That means because the slopes are the same. If one of the slopes were different, that would mean that eventually they would coincide. But for them to be parallel, the slopes have to be the same. So if I have two lines, L1 and L2, they are parallel only if their slopes are the same. Now there's another concept which is called, which is that two lines are perpendicular. What does being perpendicular means? Being perpendicular means that the lines cross, and the crossing of the lines generates a perfect 90 degree angle. Okay, so in this case here, we've got an angle here, and this angle that's generated between the lines here, this is a 90 degree angle. And we have, when we have an intersection of two lines where it's 90 degrees, we say that the lines are perpendicular. Now I'm sorry, now the relationship of lines that are perpendicular of their slopes is that if I multiply the two slopes, they're going to give me a -1. Or one slope is going to be in the negative reciprocal of the other slope. Okay, so if M1 equals 5 and M2 equals 5, these are parallel. If M1 equals 5, but M1 equals -1 divided by 5, then these two are perpendicular.
It always has to be negative.
Yes, it's very important, Leo. It has to be the reciprocal. When we talk about reciprocal, reciprocal means that it is the inverse.
Yes.
So it's 1 divided by the number, but it also has to be negative. Okay. So
Okay.
for example, if I've got two slopes, and that's a good question that Leo was mentioning, because it's going to be the situation. Now, if I have one slope that is 5 and the other slope is 1 divided by 5, for example, these are neither perpendicular nor parallel.
And there can be a case that the first slope is a negative. What happened with the second one?
Yes, good. Let's see that. Let's see that example. So Leo, give me any number that you want. It's gonna be Leo's example. Give me any
Positive
number.
or negative?
Give me a negative number so we can see your example. Give me
-3.
-3. So let's assume that M1 is -3, Leo. Now I want, what would be the slope of a parallel line to that one? It would be M2 equals -3. Okay.
Yes.
They are the same, so they are parallel. Okay. Now, Leo, let's assume that we have M1 equals -3. Okay, Leo. What do you think, if I want the other line to be perpendicular, what would the slope of the other line have to be, Leo?
No, I don't know. I'm guessing. I think it's gonna be 1/3
That's correct.
positive.
It's the number that we have, 1 divided by the number multiplied by -1. So we actually have 1 divided by -3 multiplied by -1. That is the same as having 1 divided by 3. Okay, and these two lines would be perpendicular. Okay, is that clear? No?
Yes, thank you.
Perfect. Now, let's do another example that has to do with these variations here. I'm going to pick on somebody. Who can I pick on? Who can I pick on? Let's see. Oops. Oh, my screen got moved here. Give me a moment. Let's see. Arturo, are you there?
Yes, I'm here.
Hey, Arturo, let's play around here a little bit with these examples. Let's assume, Arturo, now that I give me a number, any number, positive or negative, however you want.
7.
7. Let's assume that we have a line where the slope is -1 divided by 7, Arturo. Okay. What would the slope of the other line be if I want them to be parallel?
Would it be 7?
Well, what does it say there, Arturo, with the parallel lines in the first bullet?
It says L1 is parallel to L2 if and only if M1 is equal to M2. So
Okay.
-1/7 should be.
Exactly. So -1/7. If I want them to be parallel, they have to be the same. It doesn't matter if they're negative, if they're fractional, if they have to be the same. Okay. Are we okay there, Arturo? Now we're going to stay with you, Arturo. Now let's assume that I've got the same one, M equals -1/7. And now I want the slope of the other line, but I want them to be perpendicular. What would the slope be?
So it should be -7.
Okay. It's 7 because we're flipping it. So it's 1 divided by 1 divided by 7. This gives me 7. But what does the rule say here?
L1 is perpendicular to L2 if and only if M1, M2 equals to -1.
Or
equals to-
M1 equals the negative of the reciprocal. So I'll ask you again, Arturo, what would be the slope of the second line?
So if it's the negative reciprocal, it's going to be 7.
It's going to be 7, correct? Because the original one is negative already. So it's going to be 7, and these two would be perpendicular. Okay, is that clear, Arturo?
Yes. Yes.
Perfect, perfect, perfect. Great. Okay. So let's do some exercises here. Okay, I'm going to give you a couple of minutes to work on these. I'm going to give you a few minutes and we're going to solve them here in a moment. Okay. Do those two. Try to do those two exercises in your notebooks. Okay, let's let's try to do this here and we can check what you guys did. So I'm gonna jump over here to the whiteboard. So in the case of the first exercise, it says that we should find an equation for a line with a slope of 6 that goes through minus 1/2, comma 2. So the slope in this case is going to be 6. And the point, which would be x1, y1, is minus 1/2, comma 2. So we may use the point slope model to find the equation. So we've got y minus y1 equals mx minus x1. We're going to have y minus 2 equals 6 that multiplies x minus 1/2. This is going to give us x minus 2 is equal to 6x plus 1/2. And let's just do some arranging here. So we're going to have y equals 6 times, we're going to multiply this 6 by each of the elements there. And we're going to send the 2 to the other side. So this is going to be 6x plus 6 times 1/2 is 6 divided by 2, which is 3 plus 2. And in the end, we're going to get an equation which is y equals 6x plus 5. And this would be the equation or mathematical representation of that line using the point slope representation or equation. Okay. Questions with this one? Again, I don't think any of these things are new to you guys. Definitely not. Questions? Okay. Let's look at the next one. In the case of the next one, we are given 2 coordinates. It's 4, 3 and minus 2, 5. So we've got x.
I have a question.
Yes, go ahead, Leo.
The last one was just 1 point. It was.
Yes.
Oh,
This representation that we're using here, Leo.
mhm.
So let me comment this, Leo, which is important. Whenever we want to find the mathematical representation, the equation or mathematical model for a line, we're always going to need 2 things. We're always going to need 2 things. In this case, what are the 2 things that they're giving us? They're giving us a point and the slope. Those are the 2 things that they're giving us. Okay. The point and the slope. And using the point and the slope, I can use what's called the point slope representation, which is this one. This is the point slope representation to find the equation. So if we have the slope, we only need 1 point. Okay. But we're still being given 2 things. Okay. Is that clear, Leo?
Yes.
Okay. Now let's look at the next one. In the case of the next one, we're given 2 coordinates or 2 points. Point 1, which is x1, y1, is equal to, is it 4, 3? Yes, 4, 3. And then we've got another point, we're going to call it point 2, which is x2, y2, and this is equal to -2, 5. And so notice, again, going back to what I was talking about with Leo, we are, in this case, we're being given 2 points. But we always need 2 things to find the mathematical representation. So what we can do here is the following. We are going to first find the slope. So to find the slope, we know that the slope is equal to the change in y divided by the change in x. So this means that the change in y is going to be 5 minus 3. It's very important when we're doing these calculations to be mindful of the signs, okay? 5 minus 3 and -2 minus 4. This is equal to 5 minus 3 is 2. -2 minus 4 is -6. And this is equal to -1/3. Now, having the slope, we can now grab any of the 2 points, whichever ones we want, we can grab any of them and find the expression. So using the same point slope equation. So it's going to be y minus y1 equals mx minus x1. In this case, I just wrote down y1 and x1, and we're going to be using this one. However, having the slope, we could actually use any. We could use 0.2 as well. We should get to the same thing, but we're going to use 0.1. It's going to be y minus 4 equals m, which is the slope, which is 1 divided by 3, and x minus 4. This is going to be y minus 4. This is going to be equal, I'm going to multiply this here. This is going to be minus 1/3 of x plus minus 4 times minus 1/3 is going to be plus 4/3. Then I'm going to send this over here. It's going to be y equals minus 1/3 of x plus 4 divided by 3 plus 4.
Teacher, wasn't the y1 3?
You are correct there. Thank you. I think it was Leo.
Yes.
Yes, perfect. Thank you, Leo. I made a mistake here. I make mistakes. X is 4, yep, and y is 3. Thank you for that catch. And thank you for that catch before I finish the problem completely. So it's still time to correct it. So this would be y minus 3, correct. And we're sending the 3 over here to this side. Now, I'm going to bring this over here. So it's going to be y equals 1 divided negative 1 divided by 3x. And we're going to join these 2 fractions, and it's going to be plus, we're going to use a common denominator, which is 3, and it's going to be 4 times 9. And so that's going to give us the complete equation, which is going to be y equals minus 1 divided by 3x plus 13/3. And this would be the equation of the line. Okay. And actually, if we would have used the other point, we should get to exactly the same thing, by the way. This is using x1 and y1. Okay. Questions with this one? I'm going to do it with x2 and y2 just to demonstrate that we're going to get to the same thing. Arturo, go ahead, please.
Yes, why did you add the 4 plus 9 and divide by 3?
Oh, okay. So first off, the final representation we should get to always has to be y equals something multiplied by X plus a constant. That's a general model. So we're okay up to this point here, right, Arturo?
Yes.
Okay, so now what I'm doing is that I need to join these two. I need to add these two. Okay, so what I'm doing is that I'm grabbing a common denominator, which is 3. 3 divided by 3 is 1, multiplied by 4 is 4. 3 divided by 1 is 3, multiplied by 3 is 9. Okay, and this gives me this fraction down here.
I see what you did.
Okay, good. Okay, let's try this out now with the other point. Okay. Let's try this out with the other point. What I'm going to do here is that instead of using y1 and x1, I'm going to use y2 and x2. Let's see what we get to there. Use another color just to differentiate. I'm sorry. So in the case of the point slope, if we've got the slope, we can use any point. And we've already got the slope. We found out at the beginning with the 2 points. Now let's use the second coordinate with that same slope. So it's going to be y2 and x2. So now it's going to be y minus 5 and x minus 2. Okay. And that's going to give us y minus 5 here. Minus 2 is going to be positive, multiplied by the 1/3 here. This is going to be 2/3. And the minus 5 that we had on this side is now going to be over here adding. Oh, I'm sorry, I made a mistake in the signs there. Here. So minus times minus is plus, times minus is negative. Okay. And so the 2/3 that we have here is negative. This is also going to be 2/3. And it's going to be negative. The minus 5 goes to the other side as plus 5. And now what we've got is, now what we've got over here is a minus here. We're doing the same procedure. We're joining with a common denominator. So it's 3 times 2. Oh, so wait a minute, give me a moment. This is going to be, wait. So I'm going to put a plus here. So we're going to have a minus 2 here. Okay. And 3 divided by 1, it's going to be 3 times 15 is plus 15. And minus 2 plus 15 is going to give us the 13 that we've got over here. Okay, so even if we use the second point, we're going to get exactly the same mathematical expression, or the same equation. Okay, so remember, Arturo, go ahead, please.
So every time if you do x2 or x1 and y2 or y1, is it going to give you the same answer?
Well, that's an interesting question. If I understood it correctly, you have to use, so you either use 0.1, which is x1, y1, or 0.2, which is x2, y2. You can't combine, so you can't grab x1 and y2, and that would not give us the same.
Oh no, I was asking if you use one point or the other point, it's going to equal the same thing.
It's gonna give us the same thing because we got the slope using both of the points.
Okay, so it's like a good way to check for your answer.
Yep.
Okay.
So I just did this just to demonstrate that if we have the slope and we had the 2 points, we could use whatever 2 points to calculate the equation and we're going to get the same thing. And I think the thing to remember here, important that I just mentioned a few minutes ago, is that again, to represent an equation for a line, we're always going to need 2 things, either the point and the slope, 2 points, or the slope and the intercept with the x-axis. Okay, questions with this one before we move on. Okay. So let's go now to talk about quadratic equations or quadratic functions. So a quadratic function is going to be a power function, but a power function that the highest power is going to be 2. Okay. Now, there is a general representation that's actually called the canonical form of a quadratic function. And that general representation is ax squared plus bx plus c, which is basically a function that has three elements or 3 components: the quadratic one, the one that's elevated to the power of 2, the linear one that's elevated to power 1, and the constant. And each of these is associated with a constant or a parameter, which are a, b, and c in this order. As long as a is different than 0, then this is going to be a quadratic equation. The same as the linear function, the domain of a quadratic equation is going to be all of the real numbers from -infinite to infinite. Now, this is a very important concept in the case of a quadratic equation, but also as with regards to polynomials. And it's the concept of a root. So the roots, and we've already talked about this when we were working with inequalities. The roots are the x-intercepts, or are going to be the values of when f of x equals 0. So the values when f of x equals 0, that we can find in many ways. We can factor, we can do it many ways. Those are going to be the roots. And we all know this. Again, you should know this since secondary school or earlier even, which is what's called the general equation or general formula. Given a quadratic equation where I have the 3 parameters a, b, and c, I can find the roots using this expression. It's typical: minus b plus minus the square root of b squared minus 4ac divided by 2a. And the important thing here is that the roots are always going to be, there's a positive version and a negative version. If what we have here is positive, then that means that the roots are real, they exist. There are going to be intercepts. But if what we have in here is negative, that means that the roots do not exist. Or rather, to be more specific, they do not exist as real numbers. These are basically imaginary numbers. Okay. And there's many ways as well to represent a quadratic equation. A quadratic equation is going to represent graphically, it's going to represent a parabola. Okay, it's going to represent a parabola. Now, depending on the values of a, b, and c, is if the parabola is going to be facing upwards or downwards. And the highest or lowest point in the parabola is called the vertex. It's called the vertex. It's going to be either the highest or the lowest point in the parabola. It's called the vertex. If we know the coordinates to the vertex, then we can represent the parabola this way, which is called the vertex representation. So if we know h and k, can be used to represent the quadratic expression that way, which is a multiplied by x minus h squared plus k. The signs there are important, are going to be important for when we work with the parabolas and how to be able to represent them and understand their behavior, because There are certain physical phenomena that behave as parabolas. Can somebody tell me an example of a physical real life phenomena that behaves as a parabola? You should have seen that in physics to death.
rocket?
The what?
A rocket.
Well, a rocket, but a rocket, because any sort of launch of something, even throwing something, or a rocket, you're launching it, as long as you're on a planet that has gravity, some sort of gravity, the behavior of launching something is going to generate a parabola. It's actually going to be a perfect parabola. And the parameters A, B, and C actually have to do, in a physical phenomena, have to do with the acceleration and the velocity. So yeah, launching a rocket, if we launch a rocket, assuming that we're in the atmosphere and the rocket is going to finish its fuel, the rocket is going to go up and then it's going to go down. And that behavior mathematically is a parabola. If we throw something in the air or we drop something, it's going to be the same behavior, and it's represented by a quadratic equation. So good examples there. Okay. 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 Let's move on. Okay. So as we mentioned, the graph of the quadratic equation is going to be a parabola. Now, certain values of the quadratic equation representations, A, B, and C, are going to give us information about how the parabola is going to behave or how it's going to look. And basically the value A, so the value that's multiplying the x squared, depending on the sign of that value of A, is if the parabola is going to be facing upwards or is going to be facing downwards, or rather if the vertex is the lowest point or the highest point of the parabola. So if A is larger than 0, meaning if the value that's multiplying the x squared is positive, then it's a parabola that opens upward and the vertex is the lowest point. If A is negative, meaning that the value that's multiplying the x squared is negative, then the parabola is going to be facing downwards and the vertex is going to be the highest point. The imaginary line that crosses the center of the parabola through the vertex, that's called the axis of symmetry. A parabola is going to be always symmetrical to its axis of symmetry. So it's always going to be symmetrical to that imaginary line that crosses the vertex. That crosses right in the middle of the vertex, and that's called the axis of symmetry, or also the axis of the parabola. Not only the launching or the throwing phenomenon can be represented by parabolic surfaces. Also some optical effects and some electromagnetic behavior also is related to parabolic curves. So for example, a parabolic antenna that's used to capture signals, there's a reason why it's a parabolic, it has that form. And it's curious because the parabolic form, there are points that have to do with the vertex and the focal point, where if I were to bounce off any sort of signal or light source or anything like that, we're going to see that they're going to bounce around and they're going to join in one point, which is the focal point. Daniel, go ahead, please.
They're also used in architecture. They're a very strong figure. So
yeah, it's a typical what's called the I'm sorry, what's called the catenaria, which is that sort of hanging. So if I have a cable, for example, that connects 2 points, the weight of the cable is going to make the cable go down, and actually a parabolic form is created, and that is also used, as you mentioned, Daniel, in architecture and civil engineering and those sort of areas of knowledge. So remember that the reason that we're studying math, or the reason, or one of the reasons that we need to understand math, it's because many phenomenon that exist in real life can be represented or modeled using math. And so math emulates real life, and real life can be modeled through math. And so something as simple as a function that has an x squared to it can represent something in real life, which are these examples that we're giving right now. So good example there as well, Daniel. Okay. So let's look at these graphs. Let's look at these two examples here. So it says graph x squared minus 2x minus 3. Remember, this is going to get somebody to talk to you in these parties. Remember, you're going to be at the party and you're going to be doing stuffs, and you're going to be sketching a graph, and somebody's going to say, wow, can you sketch anything? And you're like, yeah, give me any graph. Give me a quadratic function, by the way, and I'll graph it. Arturo, just because you're on screen, what are you studying, Arturo?
Industrial engineering and global programming.
Remember
At
that?
this university.
Okay. Wow, that must be really difficult, right? You must be really smart. The mic has dropped. Perfect. Well done. Well done. Well done. Let's look at these two examples. Let's try to do the first one. So let me clear this. Let's assume now that we've got the following function, which is f of x equals x squared minus 2x minus 3. Okay. Now, we're going to graph this. It's a bit trickier than the other ones we had, because when we had just the power function, we knew directly how the shifts were going to work and all that. But right now we have a quadratic equation that has, or we have a polynomial that we're going to graph. And so to graph a polynomial, we need a little bit more information, and the shifts and the rotations, and the reflections and all that are going to be that direct or that clear. So first off, the first thing we're going to try to do when we want to graph a quadratic equation or sketch the graph is that we want to know if it has roots. Okay, what roots does it have? Because the roots are going to be the x-intercepts, are going to be the points where the graph crosses in x. So to find the roots, we can directly use the general formula. Remember that. We can always use, by default, we can use a general formula. Let's just do that to practice. So x1, 2. So first off, this is a, and a equals 1. This is b, and b equals 2. And this is, equals minus 2, and c equals minus 3. The signs are important here. It's going to be minus b plus minus b squared minus 4ac divided by 2a. Okay. So let's find those two roots using the general formula just to practice, okay? So it's going to be minus 2 plus minus the square root of b squared, which is minus 2 squared, minus 4 multiplied by 1 multiplied by minus 3 divided by 2 multiplied by 1. This is going to be equal to 2 plus minus the square root of b squared is 4 minus 4 times 1 times minus 3 is going to be plus 12 divided by 2. And this is going to be 2 plus minus the square root of 16 divided by 2. This is going to be equal to 2 plus minus the square root of 16 is 4 divided by 2. And this is going to give me 2 values. Okay. Remember, x1 is going to be 2 plus 4 is 6 divided by 2 is 3. And then the other value is going to be 2 minus 4 is minus 2 divided by 2 minus 1. Those are the 2 roots. By the way, we could have also found those by factoring. So if we factor that polynomial, this would be equal to having x plus 1 and x minus 3. Okay. And that way we also get the x1 and x2, which are the ones we found using the general formula. So from here, we would also get that x, I'm going to do it this way. Just because I'm a little OCD. It's going to be x minus 3 and x plus 1. So this would give us that x1 is 3 and x2 is minus 1. Now,
So
why are
teacher-
these? Yes, go ahead, please.
So we can use, we can like factor anytime.
Yes. Well,
Like we
remember, I'm sorry to interrupt, Leo. Remember that not all quadratic polynomials, not all of them can be factored like this
Oh,
one.
that's what I was going to say, that we can try to factor out the function, but whenever we cannot factor, we can use the general formula.
Exactly. We can always use a general formula, but first we can try to factor it. If we can factor it, then we're going to get the roots directly. If we can't find direct factors, then we go to the general formula. Okay, that's correct. So first off, is this parabola facing upwards or downwards? And why? Is it facing upwards or downwards, and why?
Downwards, no?
Well, let me just do this because I don't want to confuse. Upwards is like this. Downwards is like this. So is it facing upwards or downwards? Remember that. How do we know that? We know that by the value of A. Is A positive or negative?
Positive.
Remember this. If A is positive, it's like this. If A is negative, it's like this. Okay. So in this case, A is positive, so it would be facing upwards. Now, how do I know where to place the graph? Well, that's where the roots come in. The roots that we just found are going to be the intersections of the graph with the x-axis. So we're going to have one intersection here in -1, and we're going to have another intersection here in 3. And there's another thing we can do. I am going to find the value of f of 0. F of 0 is going to be 0 squared minus 2 times 0 minus 3. And so f of 0 is going to be equal to -3. Now, remember, these values that we found over here, these are I'll be with you in a moment, Arturo. These values that we found here are the x-intercepts. or the roots. This value that we found over here, this value is the y-intercept. Yes, Arturo, go ahead, please.
Yes, couldn't it be easier way to find the y-intercept is just look at the -3, not have
Yeah,
to do the whole equation?
It's literally the -3. I'm just being, I'm doing the procedure as explicitly as possible to know where we got there, but it's literally going to be C. If we have this representation, then the y-intercept is going to be C. Okay, which would be the -3. So that's a correct observation. And so that would be over here. 1, 2, 3. And so the person you're trying to talk to is like, wow, how did you do that? So, and you're like, well, yeah, this is easy. The parabola looks like this. Ugly parabola. Sorry about that last part. It's going to go something like this. Okay. Now we haven't found, notice that that -3 where I put the little cross, that's not the vertex. We haven't found the vertex. We haven't found the vertex, or meaning the lowest point. We haven't found that. But that's going to be on the next episode. We're gonna talk about that next Tuesday because we're just on time and you guys need to get to your Spanish class. So let me save this. A moment here. And there we go. Okay.